All right, so today we're looking at just-in-time 6.1, 6.2, and 7.1. Okay, so we'll first introduce a new family of functions called exponential functions. So exponential functions have this form, f of x is equal to a to the x, where a has to be a number bigger than 0. Okay, any number bigger than 0. And a is called the base. Okay, so for example, if we've got our function f of x is equal to 2 to the x, okay, we can graph it, so we can pick some points. Okay, let's just pick the x values, -1, 0, 1/2, and 2. Make it easy. Okay, so we plug these into our function, so we have 2 to the -1, which is just 1/2, 2 to the 0, which is 1, 2 to the 1/2, so square root of 2, and 2 to the 2, so 4. Okay, and we can graph them. Okay, so we get -1/2, so about here. 0, 1, 1, half, square root of 2, so about here. I can estimate that one. And then 2, 4. Okay, and then so we'll fill it in. Okay, so exponential functions always have this shape, and they always have a horizontal asymptote. At y equals 0. Although if any transformations happen, then it obviously moves with them, but exponential functions generally always have that asymptote there, and that same general shape swooping. Okay, the base a just determines whether or not it's exponential growth or decay. So if a is greater than 1, so like 2 to the x was, okay, your function will grow like this, swoop upwards. If a is a fraction, so a is between 0 and 1, it'll decay. Okay, or just swoop downwards. All right, so there's exponential functions. There's a special type of exponential function, e to the x. Okay, so e, before we look at the function, e is just some irrational number, okay, whose exact form is this, but you really just need to know the approximation and that e is a number and not a variable. Okay, and so then we have the exponential function. So e is the exponential number. E to the x is our exponential function, or the natural exponential function. Okay, and there's its expanded form and what it represents. And something to remember when you're graphing, so this exponential function is a 45-degree tangent at x equals 0. And then just kind of a special, so we can actually use the exponential function, and we can write any exponential function as the natural exponential function with some extra number in there. Okay, so graphing, just so you can see the comparison. Okay, here's a 1. So when we say e to the x just has a 45-degree tangent, that means that it's going to have this, the tangent's going to be at a 45-degree angle at that point. But that's not, we're not as concerned about that. But so we've got e to the x, which is about e to the 1 is going to be a little bit above 2. Okay. And then we've got, so there's e to the x. We can also graph 2x. So 2x is going to be a little above e to the x when x is -1, and it'll be at 2 when x is 1. Still going through that 0.11. They'll all go through the 0.11. So that's 2 to the x. Okay, and then lastly, 3 to the x. Be about 1/3 here. And 3 up here. Okay, so you can kind of see, so they'll all go through the 0.01. And you can remember that because anytime you take anything to the 0 power is going to be 1. Okay, and then for our 0.1, so as our a increases, okay, our values for -1 get closer to 0. And our values for 1 get further away from 0. Okay, that's just kind of something to keep in mind if you're asked to graph multiple ones, or just seems to see how they relate to each other too. Okay, and they all follow, so all the exponential functions follow the typical rules when performing transformations of functions. So, meaning if I'm given these two, so I'm given 3 to the x minus 1 and 3x minus 1. Okay, our parent function is still 3 to the x. Okay, and so then we've got okay 3 to the x minus 1. All right, will be 3 to the x shifted right 1. Okay, so where before, so our parent graph was 3 to the x. So it would have had a point here. At 1, and it would have had a point at 1, 3. Okay, with the asymptote here. Okay, so shifting right 1, we'll just shift everything to the right 1. And our asymptote doesn't change because we didn't shift up or down any. For our up or down shift, so 3x minus 1, we're shifting down 1. So our asymptote will get shifted down 1. Okay, and then everything else will too. So our points get shifted down 1. But it still holds that same basic shape. Okay. And likewise, all of our exponent properties hold. Okay, so I've relisted them here, and they all hold for e to the x. We can actually use these properties to solve exponential functions. So the biggest thing that we're going to use, though, when solving exponential functions is that if you have a like base, you can set the exponents equal to each other. Okay, so for example, if I've got 2 to the x minus 3 is equal to 64, how can I rewrite 64 as a power of 2? So I've got 2 to the x minus 3 equals 2 to the 6, just rewriting 64. Okay, now I have the same basis, so I can set my exponents equal to each other. So I've got x minus 3 is equal to 6. Solve for x equals 9. Okay. If we've got a sign in here, same way. So how can I rewrite 1 as a power of 10? Well, anything to the 0 is equal to 1. So I can rewrite this as 10 to the 0. Okay, and then I can set my exponents. So sine of x is equal to 0. So what x makes sine of x equal to 0? Well, any k times pi where k is an integer. Okay. And then if we've got, let's see, fractions, okay, I can rewrite this as 4 to the negative 1 to the 2 minus x is equal to 4 squared to the x. Okay, and so then my exponents, multiply them. So I get negative 1 times 2 minus x is equal to 2 times x. So x minus 2 is equal to 2x. So solving for x, we get x is equal to negative 2. Okay, so all of our same properties and everything still works the same with these functions. Okay, and so then we'll switch gears a little bit and talk about composition of functions and inverse functions. So if I've got two functions, this should be a g. Okay. All right, if I've got two functions, f and g, our composition is defined as f circle g or f composed of g of x. So it's not multiplication. So closed circle. Or here, let's just do this. Open circle. Open circle is composition. Filled in circle. Multiplication. Okay. Fill that in a little darker. Just the normal dot for multiplication. Okay. Just know the difference. All right. And so f composed of g is just if we're taking g and plugging it into x. So whatever the second function is, you're taking and putting that into the first one. Okay, and so you evaluate it 2 steps. You do, this breaks it down into using separate things, but think about it this way. If I've got f of g of x, okay, so f composed with g at x. So f g of x, okay, when you evaluate this at a number, so let's say f of g of 4, okay, I'm going to do this in 2 steps. I'm going to say, okay, well, what is g of x equal? G of 4, evaluate that, whatever that is. Let's say g of 4 is 5. Well, let's do 6, so it's just not 1 above, so 6. So then we'll do f of 6. So then 6 becomes our x value, and so whatever f of 6 is, then that's what it equals to. Okay, so that's what do the inside evaluation, and then do the outside evaluation. Okay, sometimes we're not evaluating it at specific points though. We're evaluating just functions in general. So if we've got f composed of g of x with our two functions here, so I've got, that's f of g of x okay, so I'll take f of x and plug x squared into it because that's what my g of x is. Okay, color coded there. And so now anywhere in my f of x where there's an x, I'm going to plug x squared in there. Okay, so my f of x will be so anywhere there's an x, I'm going to take and I'm going to put x squared in there. Okay, and then I can simplify. So I get x to the 4th plus 2x squared plus pi. Okay, so we're done. So then we can also do g composed of f. Let's say we've got our two functions here. We want to do g composed with f of x. So that would be g of f of x. Okay, so anywhere there's an x in g of x, I'm going to plug in. So that'll be g of 1 over x plus 2. So anywhere in g of x that there's an x, I'll plug in 1 over x plus 2. All right. And then we can simplify that a little bit, not much, but a little bit. So it'll be 1 over x plus 2 squared minus 1. Okay. We can also read function composition off of graphs. So let's say we've got a graph of these functions here. And let's say we want to do f of g of 2. Okay, let's say f of x is our blue function and g of x is our black function. So g of 2, we'll do that first. G of 2, so g of x when x is 2 is equal to 5. Okay, so we have f of 5. F of 5. So then f of 5, when x is 5, f of 5 is equal to 4. Okay, or we could do g of f of 2. Let's do that in a different color. G of f of 2. Okay, so f of 2, so when x is 2, f of 2, or f of x is equal to -2, so it'll be g of -2 that we do. G of -2, when x is -2, g of x is equal to +2. Okay, coming from these 2 points. All right, now something to realize or to note. So g of x, or f of g of x, is not necessarily the same as the reverse. Okay, they don't have to be the same. And a lot of times they won't be the same. In fact, there's a special case, so when they both equal x, then we know that f and g are inverse functions. Okay, and we'll talk about inverse functions a little bit more later, but just kind of know they're connected to composition. All right.